Okay, so this is the first question. So let's read the question at first. Consider a flat plate. It is positioned inside a wind tunnel, and the air properties is it is at 180 and 20 degrees centigrade temperature. Is flowing with a free stream velocity of 60 meter per second. So far what we know, we have a flat plate. It is positioned inside a wind tunnel, and the air properties, we have to calculate the properties for ATM and 20 degrees centigrade temperature. So free stream velocity is 60 meter per second. So now the question is, what is the minimum length of the plate necessary for the Reynolds number to reach 2 × 10 to the power 7? And if the critical Reynolds number is 5 × 10 to the power 5, what type of flow regime would be airflow experience at 2 meter from the leading edge? So this is really this is not a difficult problem. Let's say, okay, this is the flat plate. Okay, so let's say this is the flat plate, and we actually don't know the length. So this is the the leading edge, this is the trailing edge. Okay, and the air, let's say this is the free stream velocity is this, it is moving this way. So this is the free stream velocity, which is given 60. Okay, the free stream velocity is given 60 meter per second. So now let's say this on, it is actually the air, 20 degrees centigrade temperature. So this is actually the atmospheric air at 20 degrees centigrade temperature. It is flowing this way, and the velocity is 60 liter per minute. Sorry, the velocity is 60 meter per second. So it is given in meter per second, the velocity, not the flow rate. Alright, so we actually don't know the length of this flat plate. Okay, we don't know the length of the flat plate. So if you can remember, I showed you the theory is actually when the flow will be the turbulent. Okay, so we already discussed during our lecture what is laminar flow, what is turbulent flow, and when the flow will be turbulent. So it actually depends on the Reynolds number. We know the critical Reynolds number is 5 × 10 to the power 5. Yeah, you see it is given here, the critical Reynolds number and 5 × 10 to the power 5. So the question is, what is the minimum length of the plate necessary for the Reynolds number to reach 2 × 10 to the power 7? So you can clearly see here, this is 2 × 10 to the power 7, which is greater than the critical Reynolds number. So that means the flow will definitely be turbulent at that point. So let's say this is the flat plate, and if we say that okay, the flow will be, maybe just, we don't know, let's say the flow will be turbulent here, and the flow, no, let's say the Reynolds number will be 2 × 10 to the power 7 here, okay, at this position. So that means, according to the first part of discussion, we need to calculate the length of this length. Okay, so what is the minimum length you need for this the Reynolds number 2 × 10 to the power 7? So that means we will calculate the Reynolds number, the length. So what we know from this question is, we know the Reynolds number, okay, we know the free stream velocity, and now we need to calculate the length L. Okay, so this is the first question, and later on we will solve the second part of this question. So let's what I said in my last class, and I'm telling again, when you will solve any problem, especially for heat transfer problems, we need to write down some assumptions, because for most of the question we can't consider all the realistic aspects. So we will try to make the question simple, that what I explained in my last class. So here actually this is very simple, you don't need to negotiate with some real aspects. So what we're telling here is, but in reality maybe this condition could be different. What we are telling here is isothermal condition exists, between the flat plate and fluid flow. That's the main assumptions here. And we're talking about the properties. So we said, okay, properties are constant. So that's our assumption. If you can remember from the theories, when I explained the theories, actually during the lecture we said the definition of the Reynolds number. The Reynolds number is a non-dimensional number. Okay, it depends on the velocity. Okay, the free stream velocity, the length, the characteristics length, and kinematic viscosity. This is, we know from the theories, this is just one definition of the Reynolds number. Alright, so that means the Reynolds number depends on velocity and the length of the domain and the kinematic viscosity. Again, yeah. So here we already know this Reynolds number. It is 10 to the 2 into 10 to the power 7. The free stream velocity, it is given 60, isn't it? We need to calculate the length. So that means we are looking for this value and we need this this kinematic viscosity nu. Okay, so we need this kinematic viscosity. So from the properties, here air is at 20 degrees centigrade, so we will calculate the properties. So this is the kinematic viscosity of the air at 1 atm and 20 degrees centigrade temperature. We got it from the table A15. You will get this table from your book appendix. So we got this value. So now, how much length we need to raise this temperature, the Reynolds number 2 into 10 to the power 7. So what we did here, we just wrote the definition of the Reynolds number, the expression of the Reynolds number, which is VLC over nu. We know Reynolds number is this. Okay, the Reynolds number is this. We know the kinematic viscosity is this, and free stream velocity is this. So if we simplify this equation for LC, you see it will be LC equal, you do some cross multiplication, so it is the Reynolds number, kinematic viscosity over the free stream velocity. Substitute all the values, like the kinematic viscosity, Reynolds number, and the free stream velocity, then we will get this length. So that means we need actually this length 5.053 meter to achieve this Reynolds number 2 into 10 to the power 7. So that's the required length. So that means you actually need that length 5 point something to reach this Reynolds number 2 into 10 to the power 7. Okay, so this is the first one. This is a very easy question. Maybe this is important for your quiz 2, because definitely this week lecture will cover quiz 2. Anyway, so the second part of the question is, if the critical Reynolds number is 5 and 10 to the power 5, what it actually means I already explained. That means the flow will become turbulent at this Reynolds number, the 5 into 10 to the power 5. This is called the critical Reynolds number. So up to this Reynolds number, the flow will be laminar. At this point, the flow will become turbulent. So the question is, if the critical Reynolds number is this, what type of flow regime would the airflow experience at 0.2 meter from the leading edge? If you can remember, guys, I've already told you this is actually the leading edge. Okay, this is the leading edge, this is the trailing edge. So we just calculated this distance is 5.053, and here the Reynolds number is 2 into 10 to the power 7. So this distance is 5.053. Okay, now it is the distance from the leading edge. Now question is at 0.2 meters. So let's say this 0.2 meter is maybe here, somewhere here. Let's say this is 0.2 meter. The question is, what should be the flow regime? So in general sense, we may think that, okay, if at this distance 5.05, the Reynolds number is 2 and 10 to the power 5, so maybe it will be less than this value. So if the flow is definitely the flow is turbulent here because it is 10 to the power 7. In general sense, we may say this is laminar, but we can't say appropriately. So what we need to do, we need to do some calculation. We will calculate, okay, we will calculate it at first, and then we will see what is the actually flow regime. So what we did, we will calculate the Reynolds number. Okay, we'll calculate the Reynolds number. Say when the LC, that means the characteristics distance, is 0.2 meter. Okay, when it is 0.2 meter, then the flow regime will be, we will calculate the Reynolds number. So we generally know the Reynolds number formula is equal to the velocity, free stream velocity, characteristics, length, and kinematic viscosity. We substitute all values, and what we found is, it is, you see, 7.92 and 10 to the power 5. So this is definitely 7.92 and 10 to the power 5, 10 to the power 5, which is definitely greater than the critical Reynolds number, isn't it? So this 10 to the power 5, it is greater than 5 into 10 to the power 5. It was the critical Reynolds number, and our calculated Reynolds number at 0.2 meter from the leading edge is greater than this critical Reynolds number. That means this flow, it will be turbulent. Okay, this flow at this point, it will be turbulent. You see that what we said, which is greater than the critical Reynolds number, so the flow is turbulent. Okay, so what we found at this point, we thought it is the Reynolds number will be here, so we calculated that length. And now from the leading edge at 0.2 meter, the flow, we found it is turbulent because the Reynolds number is greater than critical Reynolds number. So that's actually the solution of this problem.